Hi, in this session we are going to look at decision tree algorithm, and we are going to use the ID3 algorithm with a numerical example. Our session is going to be in two parts. We are going to first look into the theoretical part, and then we are going to do a numerical example in a practical way. These are the issues that we are going to look at. We are going to talk about the decision tree algorithm, the ID3 algorithm. We are also going to look into the steps that one would take if you are going to use the ID3 algorithm. Then we are going to look at a numerical example of how to draw a decision tree. And then lastly, we are going to look at decision tree rules. A decision tree algorithm is a supervised learning algorithm that can be used both for classification and regression problems. Decision tree algorithm splits a node into two or more subnodes. When trying to split a node, the challenge is how to determine the root node. The process of node selection for each level is known as attribute selection. Two popular methods are information gain and the gain index. And in this session, we are going to focus on the ID3 algorithm. What is the ID3 algorithm? It stands for Iterative Dichotomy 3, invented by Ross. The algorithm leverages entropy and information gain for it to come up with the left and the right side of the branches. Dichotomization means dividing into two completely opposite things. So when we are talking about the ID3, we are talking about an iterative process whereby we are going to be dividing by two to come up with a unique or opposite items. The ID3 algorithm follows a top-down grid approach. In simpler terms, we start with a root node, but from the top, as we go down, we follow a branch where we have got the best information. So the keywords to know are entropy and information gain. When we're looking at entropy, we are basically looking at the level of impurity of a given sample. And then when you are talking about information gain, we are basically talking about the use of entropy to then find the node that gives us better information for us to then make a better decision to split the node. When you're looking at entropy, we can use the formula, the entropy of S is equal to the summation of minus pi log 2 pi, where our S is the subset node and our C is the classes in a dataset, pi being the proportion of the ith class. Given a dataset with two classes only, the value of entropy ranges between 0 and 1. If a dataset has got more than two classes, that is n classes, then entropy is between 0 and log 2n. Looking at the representation on the graph, where we have got a 0 and then 1 being the entropy, and we are saying if the proportion of the class has got an item or one side being 0, it means to say that the entropy is also 0. In an event that the proportion of the sample in a class is half, that means to say we have got equal representation of both items in the class, then the entropy is 1, that is, it is at its maximum. In an event that we have got a 1 again and a 0, as we stand there, our entropy still remains at 0. When you're looking at information gain, it is basically a metric used to determine the best node to use in the splitting. And we use Entropy to measure information gain. The method of calculating information gain can be represented as entropy of S minus the summation of cardinality of S V over S multiplied by entropy of SV, where our D represents a specific attribute or class label. And then we are looking at SV over S, which represent the proportion of the value of SV to the values in a data set of S. Entropy of S being the entropy of the whole dataset. The entropy of SV is the entropy of dataset SV. We are going to implement these formulas when we do the numeric example. Activities in the ID3, we would want to determine the root node. We have to ask the right question, that is to gain more information. Our main aim is to create purity. You also have got to know the target variable. The steps that you would take when you are iterating through this decision tree is to calculate the entropy of the whole dataset. For each attribute or feature, find the entropy. Then use the entropy to find the information gain at each attribute. Find the feature with the maximum information gain and add it as a root node or the next node. Repeat the process until we reach a desired tree. These are the steps that we're going to be looking at as we iterate through to create our decision tree. Now, given an example where we have got the weather data set which determines whether we are going to play cricket or not. As we look at this data set and example, we will see that we first of all have got to identify the target variable, which is to play. Once we have identified the target variable, we then calculate the entropy of the target variable, which is the whole dataset. And then from there, we can then go on to calculate the entropy of each of the 4 attributes to determine which attribute gives us more information, and that attribute we then make it a root node. This is our next step. And our required outcome is to draw or to come up with a decision tree as the one displayed. So let's now look at how we can come up with such a decision tree, and the decision tree rules that we are going to come up with after we have come up with the decision tree. So let's start the calculation of entropy on the whole dataset using our algorithm. So I'm just going to copy this formula and bring it down, and then do the substitution there, which gives us just before I do that, let me just, for presentation's sake, say S, and then look at the proportion of S, right? The representation of the values of S, where we are looking at the entropy of the whole data set being the target variable. So the target variable has got a total number of 14 days or rows as represented in our table there. Then we want to look at the number of days which has got a value of yes. So we're going to get a 1, 2, 3, 4, 5, 6, 7, 8, and 9. So we have got we're going to represent that with a 9 plus, and then the remainder of that from 14 gives us 5 being the decision not to play cricket, right? So we then go for and do the substitution, where we are going to get a 9 divided by 14, which is the total number of days, log 2 of 9 divided by 14, and then we do the same for the negative or the no, which is now 5 divided by 14, log 2 of 5 divided by 14. This should give us a value of 0.94. So 0.94 there becomes our entropy for the whole data set. So the next step, once we have calculated the entropy of the whole data set, is then to look at these individual features, to look at their information gain, so that we select the next node or our root node. So we are then going to consider outlook, temperature, humidity, and wind. That's how we are going to do it. So let's consider outlook feature, and then while we are at outlook, we then want to consider the values which are in outlook. And if we are going to look at the table that we have there, we have got the following values: sun, we have got overcast, and then we have got rain. So for each of these values, we then want to calculate the entropy. So let's go ahead and then look at the subset sun, and let's look at the proportion of sun. And if we are going to count the number of rows or days in which sun appears, we'll see that we've got 1, 2, 3, 4, and 5, a total of 5. However, out of the total of 5, we also want to consider how these 5 days contributed to playing cricket or not. So if we're going to look at the rows where we have got sun and its contribution with a yes, we see that we've got 1 and we've got 2. So we then want to represent the 2 days in which cricket was played as positive. So I'm going to do a 2 plus, and then out of the total of 5, that means to say 3 no. So on 3 days we could not play according to the outlook. So once we have got that figure, we then proceed on to do our calculations where we have got 2 divided by a total of 5. So take note, when we are dealing with the entropy of the whole data set, we were looking at the whole number of rows or number of days, which gave us a total of 14. So we're dividing the outcome of playing cricket by the 14, and also we went on to also include 5, which is the days in which cricket was not played out of the 14. However, this time we are now considering outlook, and we are on subset sun. Therefore, the number of total rows in which sun is gives us a total of 5. So we are going to use 5 as the denominator there. So let's proceed and do a log of 2 divided by 5. So we go on to now consider also the no, which is 3 divided by 5, and log 2 3 divided by 5. If we do the calculation, we are going to get a value of 0.971. Okay. Right. Let's just give that a little build there. And we also want to look at overcast. And let's look at the proportion of overcast. How many rows or how many days do we have in overcast? We've got day number 3, day number 7, and then day 12 and 13. This gives us a total of 4. And then we want to see what is the outcome of playing cricket when we have got overcast. We have got yes, and we have got yes and yes. So on the 4 days where we have an overcast, then cricket was played. So let's represent the proportion there by then saying 4 positive and 0 negative. So we continue with our formula to calculate. So this will be 4 divided by 4 log 2 of 4 divided by 4, and then we also go ahead and do the negatives, which is 0 divided by 4 log 2 of 0 divided by 4. This will give us a value of 0. Right. While we are here, we then want to consider a 2-class presentation of our graph that we earlier on looked at, and where we were saying if one of the proportion is a 0, or during on the proportion we have got a 0 there, there's no need for us to calculate, because if we're looking at that, it means to say that this class is already pure, right? So there's no need for us to calculate, and wherever we have an entropy of 0 there, it means to say we cannot further divide that branch, and it means to say that we have reached a leaf. So in this case, we just had to do some calculations for demonstration purpose. But wherever you have a proportion in whereby we have 1 on the other side, if it is a 2 class, then you do not need to calculate. You just have to know that it is a pure class, and pure class is at 0. Then we proceed to do the calculations of rain, right? And let's look at the proportion of rain. How many times do we have rain? We see that we have got rain day 4, day 5, day 6, day 10, and day 14, which gives us a total of 5. And out of this total number of 5, if we're going to consider the years, we see that day 4, day 5, day 10, I've got the yeses, so we have end up with 3 positive and 2 negative. If we're going to do the calculations there, we then end up with 3 divided by 5 log 2 of 3 divided by 5, and then we consider the negatives, which is 2 divided by 5 log 2 of 2 divided by 5. This is almost equivalent to the first set there where we got sun, so the value will also become 0.71. So these are the values of the entropies at outlook. Once we have calculated these values, the next thing that we want then to do is to calculate information gain. So we want to calculate information gain, right? So to calculate information gain here represented as IG. We then want to say IG of outlook, right? We want to consider outlook, and this gives us taking from this formula that we have. Let's just take that and bring it down. Okay, makes sense. So let's just move this screen up a little bit, and so we are going then to say IG of S, and then the D there is our outlook, so outlook, and then we can go ahead and do the substitution. So the entropy of S there less the summation of the cardinality of SV and multiplied by the entropy of SV. So we are then going to get 0.97, which is the entropy of the whole data set there that we have calculated on top here, right? So we take that, and then we proceed to say let's the SV, which is our 5, taking at sun here, right? Looking at sun there, where we have 2 plus 3, this gives us a 5, divided by the total number of days that we have in the whole data set, which is 14, multiplied by the entropy of sun, which is 0.97. So let's just say multiply by 0.971, and let's just leave without that, and then we close that. and let's see what we have. Right, that's correct. Let's then proceed to do the same for the next value, where we have got 4 there, overcast. 4 divided by 14 multiplied by 0, which is the entropy of overcast. Then we proceed to do that for the last, which is rain. And when we look at rain, a total of 5. 3 plus 2 here gets us a 5. So 5 divided by 14 multiplied by the result, the entropy 0.97 of overcast, 971. This should give us a value of 0.2464. This is then the outlook, the information gain of outlook when we are considering the whole data set. So we have got that value. We then want to do the same for the remaining features, which is temperature, humidity, and wind. So let's consider temperature, and just the same way we did with outlook. So let's say temperature, and we look at the values under temperature. We have got hot, we have got mild, and we have got cool. So we are also going to do the calculations of entropy for all the values of temperature there. So let's go ahead and calculate the entropy. So we go ahead and say sun hot, S hot, which is the whole data set at hot, and then we want to consider the proportion, and the proportion of hot. If we're going to look at hot, we have got hot 1, 2, 3, and 4. So we've got a total of 4, and then we want to see how it contributes to playing of cricket. If we're going to consider, we have got yes 1, and the other yes 2. So we've got 2 out of the total of 4. We have got 2 yes and 2 no's. So let's represent that and say we've got 2 positive, and we also have got 2 negatives, which is represented by the no's, a total of 4. And then we proceed to then do the calculations there to get the entropy, where we then say 2 divided by 4, which is the total that we have there, then log 2 of 2 divided by 4, and then we also do that for the no's, which is the negative represented. So we also have got 2 divided by 4 of log 2, 2 divided by 4. If we do the calculations there, it should give us a 1. Why a 1? Remember what we said, if the proportion is as a half, where we have got equal proportions there, so it's half. This is the highest position of impurity, and therefore the answer is definitely 1. There's no need for you to calculate. Where we have values of the proportion there are being equal. We had to calculate this just to demonstrate. Let's continue with the next value, which is mild. And let's look at the proportion of mild. How many times that mild appear in our data set? You see that it appears 6 times. And how many times do we, out of the 6 times, do we play cricket? If we are going to consider mild, 1, yes, we play. 2, 3, 4. So 4 times out of the 6 we play cricket. So let's represent that with a 4 plus and 2 negatives to equal the total number of days where we played cricket, which is 6. And then we proceed to therefore say 4 divided by 6 log 2 of 4 divided by 6. And then we also want to look at the negatives, which is the remaining 2 divided by 6 log 2 of 2 divided by 6. This gives us a value then of 0.9183. Let's consider the last value, which is cool. And let's now look at the proportion of cool. From our table there, we see that cool days of cool, where cool play was the temperature was cool, 1 and 2 and 3 and 4. So it's a total of 4, and then we want to consider the contribution in terms of playing cricket, and we see that 3 days where cricket was played where the temperature was cool, and out of the 4 it gives us a 1 negative, and we continue then to do the substitution where we have got 3 divided by 4 log 2 of 3 divided by 4. Then we consider the negatives or the no, where we have got 1 divided by 4 log 2 of a quarter. This gives us a value of 0.8113. Once we have calculated all the entropies of temperature, we then also want to then calculate the information gain. So let's just copy that and bring it down, and then we go ahead and say information gain of S temperature, right? What do we have? It gives us a 0.94, which is the entropy of the whole data set, less the value that we get from all these 3 values there. So we are then going to say 4, which is a total of 4 here that we have, divided by 14, and then the result of that we would want then to multiply it by its entropy there, which is 1. So we multiply by 1, and then we proceed to do that for the next value. So we have got the next value has got a contribution of 6 divided by 14 multiplied by the entropy that we have here, which is that value. Let's just copy it and bring it down, right? So, and then we consider the last value that we have, which is cool, which has got a total of contribution of 4 days that cricket was played where the temperature was cool. So we have got 4 divided by 14, and then we multiply by its entropy that we got there, we bring it down. This should give us a value of 0.0289. So this is now our information gain on temperature when considering the whole data set. We have calculated for the outlook, we have calculated for temperature, so we need to also do the same for humidity and wind. So that will be our next step as we look at the information gain of humidity. So let's look at humidity, and let's just go there and say humidity, and then let's look at the values that we have under humidity. What values do we have? We have got high and normal, high, and we have got normal. So let's go ahead and calculate the entropy of those branches of the high and the normal that we have there. So S high, and let's look at the contribution. If we're going to look at the contribution there, how many times do we have a humidity of high? You'll see that we have got 1, 2, 3, 4, 5, 6, and 7. So we have got a total of 7 days where we had a humidity being high. Now we want to look at the proportion of that in terms of playing cricket. How many times do we play cricket where we had a humidity of high? If we are going to look there, we are going to see that we have got 3 yeses, which is 1, 2, and then we have got 3 out of the total number of 7. So let's represent the yes with a 3, and then the remaining 4 with a negative. And we then proceed to do the substitution there, where we are going to then to say 3 divided by 7, log 2 of 3 divided by 7. And we consider the negatives, which is the days which you do not play cricket, and we see that we have got a 4 divided by 7. We do the log 2 of 4 divided by 7. This should give us a value of 0.9852. We also do the same for the normal, and we want to look at the proportion of that. How many days do we have a humidity of normal? We do the calculation 1, 2, 3, 4, 5, 6, and 7 again. So we also have got 7, and we'll look at out of those normal days, how many times did we play cricket? You see that we have got normal 1, 2, 3, 4, 5, and 6. So we have got 6 days that we played, and out of that it gives us a remainder of 1, since we have got a total of 7 where we did not play. So we go ahead and do the substitution, and we have our 6 divided by 7, log 2 of 6 divided by 7, and we consider the negatives or the no, which is 1 divided by 7, log 2 of 1 divided by 7. This will give us a value of 0.5916. Right, now having gone through all the values of humidity, we then want to calculate the information gain of humidity. So this, we then substitute those values, information gain of humidity. This gives us a value of 0.94 less the high there, which is 7 divided by 14 multiplied by the entropy of I, which we then bring down there, and then we consider the next value, and we also have got a 7 there, and that becomes 7 divided by 14 multiplied by the entropy of normal. This then gives us a value of 0.1516. This becomes the information gain of humidity. So we have gone through overcast, temperature, humidity, and we also have to do the same for wind. So let's consider wind in our calculation. So let's just say wind, and what are the values of wind? Values of wind, and under wind we have got strong and we have got weak. So let's go ahead and then calculate the entropy of those values where we have got strong. And let's first look at the contribution of strong. You see that if we're going to count the number of days, 3, 4, 5, and 6, we've got 6 days where we have got strong, and then we want to consider the outcome of playing cricket or not playing cricket, and where we have got weak or strong, and the proportion of that gives us a 3 positive, and 3 days in which we did not play give us a total of 6. So we then go ahead and substitute in our formula, and from the previous calculation that we had where we had an equal proportion, which is half there, it means to say there's no need for us to calculate, right? So we already know that the answer is 1. So let's consider week, and when we look at the number of days where we have got week there, we see that we have got a total of 8. 1, 2, 3, 4, 5, 6, 7, and 8. We've got a total of 8, and out of those 8, and we now look at what is the outcome of playing cricket. We get 6 days in which cricket was played, and this gives us a remainder of 2 days in which cricket was not played. We then go ahead and do the substitution, and this will give us a 6 divided by 8, which is the total of the proportion that we have there, log 2, 6 divided by 8, right? We consider the negatives, which we have there is 2 divided by 8, total number of days where we have got a week, and then log 2 of 2 divided by 8. This gives us a value of 0.8113. So once we have got that value, the next thing is we then want to calculate the information gain of wind. So let's bring that down, and now let's substitute Ig of the whole data set. When we're looking at the whole data set and we're looking at wind, so let's put wind there. This gives us the entropy of the whole data set here that we have of S is 0.94 as we calculated initially, 0.94, and then we have to consider strong there, and the number of proportion of strong there is then 6 divided by the total number of all the rows of the whole data set, multiplied by the entropy, which is 1, and then we also consider the next value, which is gives us a total of 6 plus 2, which is 8 divided by 14, and then multiplied by the entropy of week. So we just copy that and bring it down there, and after considering those calculations there, we should get a value of 0.0478. This becomes the entropy of wind when you consider the whole data set. And now we want to come up with a summary of the information gain. Summary IG, and when we are there, we want to consider outlook. We also want to consider the next value is temperature. We also want to consider humidity. Then lastly, we will consider the information gain of wind. So let's go ahead and take the values there. This is the value of our wind. Let's go look for information gain for humidity. Temperature. And then lastly, we want to consider outlook, information gain of outlook. So these are after the first iteration of the whole features that we have there. We then look at the information gain of those features, and we take or we select the feature with the highest information gain, and we consider that as our root node or our next node. So if we're going to consider those 4, we see that outlook there has got the highest information gain. So we select that as the next node, right? So this means to say that now we can represent our decision tree. We can represent our decision tree as starting with outlook. So as we draw our tree according to the Shannon method that we have there, you will see that it gives us a nice starting point, where then we will say this will be our node, the outlook, and then out of the outlook we have got 3 values, which is sun, overcast, and rain. So we draw the tree with its branches, and then we need to then say, okay, can we start at sun, and then at sun we now need to iterate again and now consider the remaining features, which is temperature, humidity, and wind, to see how they contribute on a sunny day. We then also continue to do the same for overcast, and we do the same for the rain feature. So that's how we continue to draw the tree. So considering sun, let's say at sun, when we are at sun, we now want to then look at temperature. Which has got the values. What are the values that we have for temperature? We have got hot, we have got mild, we have got cool, right? So we want to calculate the entropy of hot, mild, and cool while we are at sun. So our data set there has shifted from being the whole data set to only where we have got outlook sun. So what we need to do is we go to our whole data set there and we consider only days in which we have got sun, which has gotten 2, 3, 4, and 5. So that gives us a total of 5 days where we've got sun. So for representation there, what we do is we extract only these days and we consider the days so that our data set is somehow reduced. So we end up with day 1, day 2, day 8, day 9, and day 11, which has got a sun. So now we want to consider hot and sun. And in our previous calculations there, we had the entropy of sun. If we go where we calculated outlook sun here, the entropy of sun was 0.97. and the entropy of the whole database was 0.94. So we are now going to consider the entropy of sun. Okay, so let's go ahead and start the calculations. So we are here. We need now to calculate what, and let's look at the proportion of contribution of what. So how many times that hot contributed, and we are going to look at considering the 5 days there. We've got 1, 2, 2 days, and out of the 2 days, how did it contribute to the outcome? It contributed by giving us no. So we have got 0 yes, and we have got 2 negative, so it's total of 2. Then we go ahead and substitute in our formula, where if we have got a 0 there in the proportion, there's no need for us to calculate, so the answer automatically becomes a 0. So let's consider the next value, which is mild, and let's look at the contribution proportion of mild there. If we're going to look at that, we will see that we have got a 2. Let's look at the outcome. The first mild gives us a no, the second mild give us a yes. So that means to say it's an equal representation of a 1 yes and a 1 negative, which is a no. And when we have got equal representation there, it means there's no need for us to calculate. We just know that it is impure. It is a maximum level, which becomes 1, where we are dealing with 2 class. So we continue to the next, which is cool, and then we say what is the proportion of cool. If we're going to look there, we only have 1 where it is a yes, so it is a 1 plus represented with a 0 negative, and wherever we have got a 0, there's no need for us to calculate. We know automatically the answer will become 0. So having calculated those values, we then need to calculate the information gain. While we at this time, we are now at dataset sun, and we are looking at temperature. So I did that so that we can know and understand what it means and what is the effect of being at sun. So when we are at sun, we then want to get the entropy of sun, which is this value that we have represented there. So we bring that 0.971. So we are now using 0.97, the entropy of sun, instead of using the entropy of the whole data set, right? And then we go ahead and do the calculations. When we are looking at that, then we now need to say, okay, 0 plus 2 gives us a 2. Now, instead of dividing by 14, which is the whole dataset value rows, we now divide by 5 because sun appears 5 times or 5 days in this sub dataset. So it's now divided by 5. This is key, what we always have to remember. And then we do a log of 2 divided by 5. Then we, oh sorry, that's not log. We are then multiplying that by the entropy, which is 0, right? And then we do the negatives, where we also consider the next value, which is again a 2 divided by 5, and this time we are multiplying by 1, which is the entropy of mild there. And then we proceed and also do another value, which is 1 divided by 5 and multiplied by 0, right? So this should give us a value of this should give us a value of 0.570. So that's our information gain while it's at sun and we are looking at temperature. We then have to do the same while it's at sun, calculate the remaining features, which is wind and humidity. So let's go ahead and do that calculation at sun, and we are considering humidity, and we are looking at the values of humidity, which are high and normal, high and normal. So let's just give that a bold for presentation. And we want to calculate the high, entropy of high. We also want to do entropy of normal with its representation. So let's start with the high and see what we find that the proportion there. If we are going to consider high, we see that high has got a total number of 3, and in those 3 days, when we are considering Sunday, the outcome of playing cricket was no, so it's a 0 positive and a 3 negative. And wherever we have got a 0, we already know the answer of the entropy becomes also a 0. And now let's consider normal, and if we go, we've got 2 days of normal, and all outcome was yes, so we have got 2 positive and 0 negative, and again the entropy automatically becomes 0. So we proceed to calculate the information gain while it's at sun, and we are considering humidity. This will give us, and we are considering the entropy of sun, which is 0.971, and Then we want to consider those two values there, which becomes if we add 3 plus 0 plus 3 there, we get 3 divided by the total number of days or rows where we have got a sun, which is a 5, then multiplied by the entropy, which is 0, and then we also do the same for the next value where we have got a total of 2 divided by 5 multiplied again by the entropy of 0. This then gives us a value of 0.97 with this one again, which is still the same, right? So we have managed to do the humidity, the calculation of the information gain of humidity. We also need to do the same for the last feature, which is wind, while it's at sun. So let's go ahead and say at sun, and we are considering wind feature. And what are the values of wind? We have got weak and strong, so strong and weak, and let's just give that a bold for presentation. So let's go ahead and then say consider strong, and then also consider weak. Right? What is the proportion of strong and weak? So start with the strong. If we're going to consider strong, we've got 1 and 2, and we have got 1 day yes and 1 day no. So it is 1 1, which will give us a total of 2 days. 1 positive and 1 negative, and wherever we have got an equal representation, automatically the highest level, maximum level of impurity, which gives us a 1. And then we also consider the weak, and we look at the weak there. We have got 1 2 3 and total of 3, and only 1 day was a yes, so we've got a 1 yes, which is a positive, and 2 negatives to give us that value. And then we want to do the substitution at wind. That gives us a value of 3 of 1 divided by 3 log 2 of 1 divided by 3, and then we consider the negative, or the days we did not play, which becomes 2 divided by 3 log 2 of 2 divided by 3. This gives us a value of 0.918, and now let's calculate the information gain of at sun, and we are considering wind. This using the entropy of sun, which is 0.7, less where we have got a 2 divided by a total of 5 and multiplied by the entropy, which is 1. Then we consider the next value of weak, which is 3 divided by 5 multiplied by the entropy, which is 0.91. This then gives us a value of 0.0192. That is the information gain. And then we want to come up with a summary. Summary information gain while it's at sun. and we consider temperature, we consider humidity, and then we consider wind. So let's take the value of wind, information gain of wind, information gain of humidity, and then lastly information gain of temperature. So if we are then going to consider these values there, and we want to pick the one with the highest, you see that we are going to consider 0.97. So this one becomes next node. Okay, so we then want to, while we are at sun, so we then want to draw our decision tree while we are standing at sun. So we have discovered that the next node is humidity. If we just go and check on the humidity while we are dealing with sun, and we are looking at the entropy of high and normal under humidity. So let's go a step up and consider humidity there. Whilst we're calculating the entropies of humidity, we also discovered that the entropy of high and normal are 0, which means to say we cannot further split those values there. Meaning to say wherever we have got a high, the outcome still remains the same. It is not going to change. It was if we're going to look then out there, you see wherever we had a high, the outcome was a no, and wherever we had a normal, the outcome was yes. Mean to say, as the entropy was 0 there, we cannot further split at that point, and while it's at sun, so the value there remains what it is. So graphically, we are going to represent this as follows. So now this is our decision tree. While we are standing at sun, the next node is humidity. And we also discovered that while you take the next node as humidity, it has got two values, which is high and normal. And while you are at a high, the decision there is always a no. So this branch, we cannot further split it. We take the second branch, which is a normal. Again, we discover that wherever we have got a normal, if we are basing on sun, the outcome of that is always to play cricket. So the other features there do not matter wherever we are going to have a humidity of high, and we are coming from the outlook where it is sun. So where there's a combination of a sun and a high, it doesn't, the temperature of the wind features do not matter. The outcome of that is always to not play cricket. And wherever we have got outlook and humidity is normal, temperature doesn't matter, and even the wind status doesn't matter, we are always going to play. So this, as far as this branch from outlook to sun and humidity, we have complete drawing the decision tree. So you can see from here we can already come up with some decision rules. But however, we are not done, so we are not going to consider also the other leaf, which is out of the outlook, which is overcast, and see how it presents itself. So let's go ahead and consider, look at the values of overcast whilst we dealing with the whole data set. So if we just scroll up a little bit and go to the whole data set and look at the outcome of wind, of outlook overcast, So let's go Outlook and then we consider overcast. Whilst we were calculating the entropies of overcast, we also see that the value, the entropy there is a 0, meaning to say when you are coming from Outlook and we are considering overcast, which is Outlook the main root node, and we are considering overcast, the outcome there automatically the entropy reached its leaf. We cannot further split. So what we just need to do is to go to the whole data set and consider to see what happens when there is an overcast Outlook. Cricket was played, overcast, cricket was played, overcast, cricket was played. So it means to say we cannot further split that. So automatically, considering those values, it means that our node tree there, we are then going to say that overcast here we are going to play cricket, right? So let's say at overcast, and then let's just put some notes there. And we are saying the entropy for whole data set, when overcast. So the entropy of overcast on the whole data set is equal to 0. We cannot split it. So after considering that, we then want to represent that. Let's just give another information. On all days where Outlook is overcast, cricket was played, right? So to represent that, we then put down this graphical representation. Okay, so this is what we have. Wherever there is an overcast, according to the results that we have there, we always play. So the next thing that we want to do is to now consider Outlook rain and see what we are going to do with those values. So let's go ahead and calculate while it's at rain. So we then want to say when Outlook is rain, which days do we have rain? We have got day 5, day 4, day 5, day 6, day 10, and day 14. So we take out, we select those days and represent them. We have day 4, 5, 6, 10, and 14. And then we restart the process again and we are considering temperature because we are at Outlook rain. So we want to look at the 3 remaining features to determine whether we play cricket or not. So, and looking at those, we have got the values the values of temperature, which are hot, mild, cool. So let's go ahead and restart the process of calculating the entropy represented by the proportion there. If we are going to count the number of times, it's also 5 rows, 5 days that we have. And how many days do we have hot? If we're going to look at the temperature there, and how many days do we have hot, to see that there's no we don't have hot, so we're going to represent that with the plus, and also with 0 negative, and wherever we have got a 0 there, it automatically gives us also a 0. And we go ahead and do mild, and the representation of mild there, if we're going to look, we have got 3 times that it appears, and on 3 times we have got 2 yes and 1 no. So let's represent that with a 2 plus and a 1 negative. This then gives us a value as we calculate of 2 divided by 3 log 2 of 2 divided by 3 with a negative of 1 log 3 divided by log 2 of 1 divided by 3 to give us a value of 0.918. Then we go to the last value, which is cool, and look at the representation of how many times cool appear there. We can see that it appears twice on those 2 days that it appears, day 5 and day 6. On day 5 we played, and day 6 we did not play, which is a 1 yes and 1 negative no. And wherever we have got 1 and 1 which are equal, that means say they have proportion, and therefore entropy becomes 1, and we go ahead to calculate the information gain and of this time it's now rain, and we are dealing with temperature. We therefore want the entropy of rain, so we need to go and get the entropy of rain. So let's just scroll up and get the entropy of rain on the whole data set. Right, it is 0.971, so it is the same as the entropy of sun. So let's bring that down, and we have got 0.97. Then we consider the 3 values that we have there, right? And our first value is 0 divided by the number of days where we have got rain, which is 5. We multiply that by the entropy, which is 0. And then we now want to consider mild. And when we're considering mild, what do we have? We've got 3 divided by 5 multiplied by the entropy, which is 0.9. And then we also want to consider the last, which is cool, and we have got 2 divided by 5 multiplied by 1. This should then give us a value of 0.0192, which is the information gain of temperature when we are considering that we are at rain. We need therefore to do the same for humidity and wind. So let's proceed and do the same for that, and say at rain, and we are considering humidity, and what are the values? The values of humidity are high and normal. We go ahead and calculate the entropy of high, and the representation there is we have got 1, 2, let's go ahead, high, yes, and then another high, no, which is a 1 to 1, so we go ahead and say 1 positive and a 1 negative to give us a 1, and then we also do that for normal, and the proportion of normal there, what do we have? Under normal we have got 3 normals, and from those 3 we've got 2 yes and 1 no, so we represent that by 2 positive and 1 negative, and that gives us a value of, just do that, representation, okay, this therefore gives us a value of a 2 divided by 3 log 2 of 2 divided by 3, and we consider the negative, which is a 1 divided by 3 log 2 of 1 divided by 3 to give us a value of 0.918. Therefore, we continue to do the calculation of information gain while we are at rain and we are dealing with humidity, and we have already found that it is a 0.97, which is the entropy of rain, and now we want to consider high. High is a 2 divided by the total number there was a 5, so multiplied by 1, and we consider the next value, which is normal, and we have a total of 3 divided by 5 multiplied by this entropy for 0.9. This should give us a value of 0.0192. So we have calculated temperature, we have calculated humidity, then the last point is the wind. So let's continue to do the same. While we are at rain, let's consider wind, and what are the values that we have for wind. We have got strong and we have got weak. So we proceed to do the calculations. And if we are going to consider strong, and the proportion of strong there, we have got 2 strongs, and on both occasions cricket was not played, so it's a 0 positive with a 2 negative, and wherever we have got a 0, the entropy becomes 0. With the calculations for for the week, and we go check the week. We have got 3, and on both conditions there, cricket was played, which is becomes 3 positive and 0 negative, and therefore the entropy is also a 0. There's no need for us to calculate. Then we go on to calculate the information gain, where we are standing at rain and we are considering wind, and with our value of 0.97, then what we are going to have there is a 2 divided by 5 multiplied by 0, and we also do the same for the week, which gives us a value of a 3 divided by 5 multiplied by a 0 to give us a value of 0.97, right? So now we have got the 3 values, so let's come up with a summary of information gain while it's at rain. And what are we considering? We are considering temperature. We are also considering humidity, and then lastly we are considering wind. So let's get the value of temperature. Information gain of temperature is 0. That. So let's bring it down. It is a 0.0192. Let's consider the humidity. Information gain of humidity. We also get the same figure. And then let's consider information gain for wind. And for wind, we got 0.97. And we bring it down. After analyzing these results, therefore, we can see that 0.9 there becomes our next node, which is wind, next node, right? So we then want to go to our decision tree and to draw our decision tree by then saying at wind, we are going to, if we go up, coming from wind, our next node here is going to be wind, right? Then whilst we are at rain, let's consider the results of calculating entropy of wind. Again, when we were calculating the entropy of both the strong and the weak, because those are the values of wind, which becomes the 2 branches from the wind, we see that the outcome there was an entropy of 0 and 0. So whenever we are at strong, we cannot further split, and whenever we are at weak, we cannot further split. So we then want to go at our data set and see what happens. Wherever we've got a wind, we play, which is whenever we have got a weak wind, wind is a weak, we play, and wherever we have got a strong wind, we do not play. So we can then go ahead and represent our decision tree, or the information of the entropy on our decision tree. So we then see that if we are at wind, rain, and then we take the node as a wind as the node with information gain. Wind has got 2 values, which is strong and weak, which becomes our branches, and we branch, and then we are at node strong while it's of the wind. And according to our results there, we cannot further split strong and we cannot further split wind. We then look at the values. So we see that wherever we have got strong wind under rain, we cannot play, and wherever we have got rain and the wind is weak, we always play. So this becomes our decision tree and the result of our calculation using the Shannon entropy, or the ID3 and the ID3 algorithm. And wherever we have reached this point where we cannot further split, which I represented with a green color there, it means that we have reached the leaf of this branch. So when you are at the leaf, you cannot further divide or climb high or low, right? This is the decision tree. The next thing that you would then want to do is to come up with decision rules. So let's see how we can create decision rules, right? So looking at this tree, we can then say rule number one. What could be our rule number one? Rule number one, we could say if outlook is equal to rain and wind is strong, then play, or we don't play cricket, or play is no. So our rule will be if outlook is equal to rain and wind is equal to strong, then play is equals to no, right? So that will be the first rule. We can all again do the second rule, which takes the other branch, where we are saying if we take the whole of this, just bring it down there, and then we change it, and we are saying if outlook is rain and wind is weak, then play is yes. So that's how you create decision rules. We could further go on and look at the overcast, and where we're saying if outlook is overcast, then the decision is always play. So we can further go on and do another rule there, where we say if outlook is equal to overcast, then play is equals to yes. So you could further go on and create some other decision rules, such as some rules such as on the sun, where if outlook is sun and humidity is high, then no. If outlook is sun and humidity is normal, then you say yes. So that's how you create your decision rules after you have come up with a decision tree. So go ahead, create the two other rules that we have using the Outlook Sun. So this is how you use the ID3 algorithm to create a decision tree. If you are new to this channel, kindly subscribe, click the subscribe button so that you don't miss future updates. Also remember to like this channel, and thank you for watching. See you in the next lecture.